not A to B, not arbitrary, from negative A to A, then that means you're going from, you know, whatever it is here, negative A to A. That would be this area, this whole area. This property is saying, you know what? You don't have to worry about the whole area. You can just do half of it, right? Do half of it and double your answer. So just go from here to here, right? That's that right there. And then double it. Does that make sense to you? Yes. Oh, yeah, I didn't see.
Yeah, isn't it the same thing you did with that cosine function then? Earlier?
With the cosine one?
No, sorry, with the sine function. Earlier.
Well, the sine, I didn't go from negative, like negative pi to pi, right? I went from 0 to 2 pi. So this property would only work if you go from the negative side to the positive side. Then you could, right? These numbers have to be the same, just opposite. Got it? All right, what is an odd function? That's the next property after this one. Do y'all remember what odd functions look like, or what odd functions are? Anyone remember the definition of an odd function? F is odd when you plug in negative x, and this is even, right? That's what it means to be even. You plug in x, you get negative x, right? That's even. The difference between even and odd is that this side is negative. They're opposite. So you don't get the same answer, you get the same answer but opposite sign. An example of an odd function is the sine function. We'll graph it. Or you know what, let's do it arbitrarily first. So this says, let's say that I plug in x and I get some value out, right? To be odd means that when I plug in negative x, right? When I plug in negative x, I should get that f of x value, but negative, or opposite. So instead of being up here, it's going to be reflected down here. So that point will be down here instead. And that'll happen for every single point. So if I have something like this, graph doing that, then this graph should do this. So that is not symmetric to the y-axis like this, right? It's not symmetric to the y-axis. It's also not symmetric to the x-axis, because symmetry on the x-axis would mean I flip it down, it would be down here, but that's not even a function. Do y'all remember what we call this? Symmetry to the origin, or with respect to the origin. This is symmetry with respect to the origin.
So tangent be one?
What's that?
Would tangent be one?
Would tangent? Yeah. Yeah. So we call this symmetry with respect to the origin. I'm just going to say to origin. I always look at symmetry with respect to the origin as a double reflection. It's basically take this reflected over the y, and then take that answer reflected over the x. That's the way I look at symmetry over the origin. You can also look at it as a rotation. Rotate like that, and you would get the same picture, right? All right. Yeah, so what would this happen? If f is odd, if we go from negative a to a, and f is an odd function, what would we get? Drum roll. Zero. Good, we get 0. Because if you go to a, let's say I go to a here, right, and then over here is negative a, and I take this area, and then I put this area over here with it, it's going to count this as negative, it's going to count that as positive, but because of the symmetry, they're going to cancel each other out. And therefore, you would get 0. There's one problem in your homework set, or sorry, you know what? I don't know if I assigned that problem, but anyway, there's a problem in the homework, in one of the exercises at the end of a section, I have to look for it, where they give you a function, and I can't even integrate it. There's no way to integrate it. It's really a complicated function. But they go from like negative pi to pi. And then you can check that it's odd. And once you check it's odd, you know the answer is 0 without doing any work. It's a tricky question because it catches you off guard. All right, I think that's it for properties. Yeah, okay, that's it. So this is the homework assignment that I normally give for the 5-point, for all these topics together. That's usually what I give. Don't feel like you have to do that, but if you want to just see what I've asked students to do in the past, those are the problems. And remember, these notes are available to you on our website. Let's just do one example before we move into 6.6. I feel like we haven't done enough examples. Let's just do one example of a definite integral. These properties that we have here, we just need to know they're there, and we'll use them as we proceed through the class. So the one I want to do is, there we go. That one right there. I want to know the net area from 0 to 2 pi of x cosine x dx. All right, we have a definite integral, right? Now, I graphed it for you just so you could see it. That has no impact on how we're going to proceed through the problem. That's just so you can see what the graph of x cosine x looks like between 0 and 2 pi. We have some positive area and some negative area there, right? This is going to give us the net area. It's going to combine those together and give us an answer. All right, first step, we need the antiderivative, right? So I need to know the antiderivative of x cosine x, which is going to require some work, right? So I'm going to come over here, and I'm going to separate myself from the definite integral, and I'm going to work on this as an indefinite integral first, right? I know I need to come back over here and do some work, but I'm going to do that first with no numbers, which is what we just spent the last how many weeks on, right? We look at that, we go, okay, 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 and we decide we're going to do it with integration by parts, right? Integration by parts. So you're going to make a table. I'm going to choose this to be my u. That's going to be my u, and then I'm going to choose all of this, to be my dv. Right? So u is x, dv is cosine x dx. Integration by parts, do I need to write that down? You all know what I'm doing here? Okay, so I'm going to do this. You have to remember this test, these things could show up, right? Integration by parts is fair game now, right? So now I finished the table. To go down, I differentiate. So du is 1 dx. And then integrate up here, v, that should be just sine x. And then I'm going to use ultraviolet minus voodoo. So this should be ultraviolet, these two multiplied, x times sine x, minus a new integral, voodoo, which is v times du, which is just sine x dx, which is a nice integral. This is x sine x minus the antiderivative of sine is negative cosine, right? So negative cosine of x, right? Plus some constant, right? Because I'm doing an indefinite integral right now. And then x sine x plus cosine x plus a constant. So that's my antiderivative, right? The fundamental theorem of calculus says now we can take that answer, right? We can take that answer and we can plug it in right here. X sine x plus cosine x plus any constant, right? I'm going to use 0. I can use any constant I want. I'm going to use 0. Is that right with y'all? Yeah. Do y'all see that if I used any other constant, it wouldn't matter? Let me show you. I'm just going to show you just in case you're having a problem with that. Let's pick a constant. I'm just going to pick 5. Okay, what if we did that? Okay, how's that going to impact things? Well, I forgot my evaluation bar. I need to plug in 0 and 2 pi, right? That's the next thing I write. And then I have 2 big old parentheses. All right, when I plug in 2 pi, I'm going to get a bunch of stuff, and then I'm going to have a plus 5, right? And that's going to go here. So I'm going to have a plus 5 in here. And then when I plug in 0, I'm going to also have a plus 5, right? And that's going to be over here. But I'm going to subtract that plus 5. So it's going to go away, right? And that would happen for any constant you ever use. So why don't we just use 0 to start with? Or why don't we use 0 all the time? Yes?
So with definite integrals, we don't need to worry about the plus c.
That's right. You don't need to worry about a plus c at all.
We don't need to record a plus c.
Nope. Nope. And this work over here, I'm not, if you're doing a definite integral, I don't even care if you put plus c here because you realize you're going to use 0 anyway. I just did it because I wanted everyone to just see the difference between what we're doing here versus what we're doing over there. We're going to use this answer over there. Oh. So I'm going to use 0 here. I'm not going to use anything, all right? So now this is going to become 2 pi sine of 2 pi plus cosine of 2 pi. And then I plug in 0. 0 sine of 0 plus cosine of 0. This has to be done in that order, right? It's the right endpoint first, then you subtract the left endpoint, right? If you get it the other way around, your answer will be correct, but you'll be off by a sign, won't you? Like maybe if you get it, if this is 4, then you would get a negative 4 if you got them backwards. Yes?
Wouldn't it be 0 then?
Wouldn't it be what?
0, like plus you.
Oh, the final answer, is it 0? I don't know. Is it? Is it? Okay. Yeah, so sine of 2 pi is 0, right? So that's all gone. And cosine of 2 pi is 1. So this is just 1 here. And then minus over here, that's gone. And cosine of 0 is 1. 1 minus 1 is 0. So what does that tell you? Yeah, that total area is 0, right? So this little piece down here, that area is equivalent to this area and that area put together, right? So I would say this was, not very useful, right? I mean, in terms of, we know that the net area is 0, but it doesn't help us figure out the areas of those. So how do you think you would figure out, if I wanted to figure out the area of each of those, what would I have to do? Go ahead.
Would you have to find the zeros of the equation?
You would have to find the zeros or x-intercepts of the equation first. So if I wanted to do that, I would have to first start by doing this. Set x cosine x, the original equation, equal to 0, right? I have to set the original equation equal to 0, original function, to try and figure out where it's hitting the x-axis. We can do this, because this is two things being multiplied. Now, I'm going beyond what we need to do. I'm just showing you, like how you would do it. You set these both equal to 0. All right, x is 0. Well, yeah, that's that first one. Let me graph it. That's the first one there, right? And then this one, what about cosine x is 0? So where is cosine 0? Pi over 2 and 3 pi over 2. And I'm only going to be looking between 0 and 2 pi. There's actually an infinite number of solutions to this, right? But I'm only looking between 0 and 2 pi. And the only answers here are pi over 2 and 3 pi over 2. I'm just thinking of the unit circle, right? Cosine's the x-coordinate, pi over 2, 3 pi over 2. Those are the two places where it's 0. So I know that at pi over 2 and 3 pi over 2, I have x-intercepts. And then you can see from the graph, I mean, we know it does this, and then that, and it goes up like that, right? And this ends here at 2 pi. That's where my interval ends. So if I wanted to know this area, right, I would do that same integral, but I would go from pi over 2 to 3 pi over 2, right? Now this would be the same, right? But this would be pi over 2 to 3 pi over 2, and then this would change. And whatever number that is would be the area. And it would be negative, wouldn't it? Because it's below the x-axis. All right, so there's a way that you could find those areas individually, but it would require some x-intercepts or some zeros. I'm not going to ask you to do that on a test, all right? I would just ask you to do the original problem, and your answer would be 0, and that'd be it. Okay, we're moving on. So we're going to go from that right into improper integrals. The entire idea of the definite integral is that we start at A and end at B, right? And we find the area underneath some function. Improper integrals are broken up into two types, type 1 and type 2. We are only going to study today type 1. Type 1 improper integrals. And type 1 improper integrals are called infinite intervals. So 6.6, improper integrals. Type 1 infinite intervals. So, as a reminder, right, what I just said, recall that what we know now is that if you want to find the area between A and B, right, we know how to do that. So long as you can find the antiderivative, right? So we're good with that. So we are trying to find the area underneath this curve on an interval. This interval is the closed interval from A to B, right? You start at A, end at B. That's the interval we are finding the area underneath, right? This type 1 improper integral is what we call an infinite interval. This is not an infinite interval. It starts somewhere and ends somewhere. What we want to do is think about what would happen if I make this interval infinite. So there are a couple of different ways I could do that. I could do, so what is an infinite interval? Well, it's an interval that doesn't have an end to it, okay? So there are a couple of types. You could have this. You could have an interval that goes from negative infinity to some point B. Right? That would be basically an interval where you go out to the left forever and stop at some right endpoint, yes? Or you could have start at some point A and then go on to the right forever to infinity, right? Or you could go in both directions forever. Those are the three types of infinite intervals we are going to look at. And now what we're going to ask is it even possible to think about like what the area under some function would be on one of these? Yes?
Sorry, wouldn't the indefinite intervals just also be like this? Wouldn't that also?
Wouldn't it also be what?
Isn't that the same as saying that this is the area without telling you exactly which one?
It's the area underneath the function, but either to the left forever, to the right forever. So let's start with this one. I'm gonna start with this one first, okay? So let's say that I have a function, okay? And I'm gonna have this function come down towards the x-axis and have a horizontal asymptote of 0. So it's getting closer and closer to 0 here. And I'm going to start this function out here at some point A. And the question is, what is the area under this, including all that area under there, underneath that part that's starting to sandwich towards 0, right? What's that area? So I think the natural question is it even possible for that to be an actual finite number, or is it always going to be infinity? What do you think? This is an important idea in this class. If this graph goes forever, if I tell you this graph goes forever and ever and ever, and it just gets closer and closer and closer to 0, never touches 0, ever, just gets closer, how is your mind dealing with the idea that the area of that is not infinite all the time? Like sometimes it could be infinite, but I'm telling you also sometimes it's not infinite. How's your mind dealing with that? Do you feel like it should always be infinite? Yeah? I mean, you're going forever, right?
But wouldn't the numbers eventually just get so small that the impact on the area is negligible?
Yeah, so as you go to the right, I would agree. If it gets smaller, the impact on the area, the amount of area that you keep adding is becoming insignificant. but it's still something, right? I mean, it's still something. And so if you keep adding something, shouldn't it get bigger? This is a fundamental question in this class. We're going to deal with this in chapter 8 again. So I'm going to give you kind of a preview, but this will help us address this question. This is kind of the classic problem here. This is a theoretical problem. Let's say I have a cup, okay? 1 cup. Okay? 1 cup. The perfect cup. It's perfectly made. It holds exactly 1 cup. All right? And now I'm going to start pouring liquid into it. All right? So I'm going to pour some water into this. And I start off by pouring 1/10 of a cup into that. Okay? So now I've got some water here on the bottom, don't I? And now I'm going to pour some more. And this time I'm going to pour in 1/100th of a cup. Does the water level rise?
Yes.
Yes? Right? Because I added something, right? So the water level comes up. It's higher now, isn't it? Okay, now I'm going to repeat, and I'm going to do 1/1000th of a cup. Does the water level rise? Yes? Again, this is theoretical. We're not talking about atoms, molecules. This is purely theoretical, all right? Evaporation, I don't want to hear any of that. This is just a theory. You have a question?
So it's more in how it relates to time. Like you could just keep doing this forever, but it's not, it doesn't accomplish anything.
Well, does it? If I keep doing this forever, what happens? Does the cup run overfill or not?
What I mean, there is no forever. There's a point where what you're doing is no, eventually will have no relevance whatsoever.
Exactly, but theoretically we can imagine doing this forever, right? I know physically I couldn't do it, right? I don't have enough time to do this forever, right? But theoretically, if we kept taking this, you know, take 1/10, add 1/100th, add 1/1000th, add 1/10,000th, I just keep adding zeros each time and keep doing that forever, is the cup going to run over or not? Is it going to overfill or not? So let's think about it for a moment, and then we're going to take a vote. The question is whether or not you think the cup's going to run over or not, like overfill. If this could go forever. Got your answer? You got a question? Questions? Ready for your answer? How many of you think the cup's going to overfill at some point? Okay. How many of you don't think it's going to overfill? Okay, let's start with the people who think it's going to overfill. Convince me. If you think this is going to overfill, convince me.
Well, even if you keep getting like smaller like denominations of what you're adding, it eventually is going to add up to 1 whole cup.
Okay.
If it's in theory and it's forever, that means it'll never end. So even if it's getting smaller and smaller, it will eventually reach it.
So even though these are getting smaller, they are all positive numbers. It's something, right? It's not nothing, it's something, right? There's some positive amount that we keep adding. And so as I do this, I'm helping you with your argument. As I do this, every time I do it, the water level comes up. Yes? It does come up each time, doesn't it?
Yes.
And if I do that forever, the people who are saying it overfills, I think their argument is that because it's something, and this is a finite cup, that eventually that water level will overfill. Okay, that's that argument. I think it's a pretty good argument. How about the other way? Go ahead. Can you have infinity with? You mean, can your answer be infinity? Is that what you're?
Like if you say the asymptote is like the last constraint, can't you just put it like time? Like it does like brackets over.
Oh, you mean not get? I'm having trouble understanding you.
There's technically an infinite number of numbers between 1 and 2.
Mhm.
You always add another decimal place.
Mm-hmm. Is that what you're saying?
Yeah, so like you won't actually ever reach the top of the cup because it's like the asymptote.
So it's like asymptotically approaching the top of the cup?
Yeah.
So you're thinking that there are things that do get bigger that never reach something. And I think maybe you're referring, maybe this isn't what you're doing, but just an idea of just like a graph of a function where you have a function that does this, right?
Yeah.
Is that graph growing? Always growing?
Yes.
Yes. Does it ever get past that dotted line?
No.
No, I like this argument. Maybe this is what's happening, right? So this is where, was there another, yes?
Eventually, you have a limitation on like how big the molecules are, so
No molecules. No, that's what we're saying. We're not talking about this because you start talking about molecules and I'm going to ask you what a molecule is and what's a molecule made up of, and you're eventually going to say, I don't know, right? This is purely theoretical. Okay, theoretical, this is, we can keep getting smaller, we can keep splitting it down, down, down forever.
I was going to ask, is there an atomic particle that, is there like the smallest amount that cannot be divided anymore?
Well, we don't know, right? We only know what we've experimented, and we've gotten to a point where we've gotten down to a certain place, and we haven't gone further than that, right? So I can't answer it, you can't answer it, nobody can answer it yet, right? So that's why I have to say this is theoretical, because I can continue making these numbers, can't I? I can continue making numbers. Now, could you actually split some, could I measure that much water out? No, but theoretically, I could do this, numerically, this makes sense. Make sense? You understand? Okay, so we had a lot of people think it overfills. I like the argument for that. And then we have people who think it doesn't overfill. We have a good argument for that. We can settle this very easily, very easily. All right, all you have to do is look at what these are as decimals. This is 0.1. This is 0.01. This is 0.001. The next one's 0.0001. And now if you start adding these together, put those two together, you get 0.11, 0.111, 0.11111, right? And you do that forever, and you're going to get what? 0.11 forever, which is exactly the fraction 1/9. If you do 1 divided by 9 on your calculator, you get 0.111 forever. So if I could do this experiment, if I could, theoretically, if I could start pouring, not only would I not fill this cup up, I wouldn't even fill it up halfway. I would get closer and closer to 1/9, but I would never get past 1/9. And if I could do it forever and ever and ever, that's essentially what 1/9 is. It's weird, okay? But did I settle it? Is everyone convinced? Okay? So in math, we start to get into places here where things become counterintuitive, right? Our intuition tells us one thing, and then we have to be able to settle it with math. We're going to see this in chapter 8 a lot. This is actually a preview of, this is called an infinite series, and this is an example of what we call a geometric series, and it is a convergent geometric series, and there's a formula that we're going to have, blah, blah, blah. All right, now that's not what we're doing here. What I was trying to get you to think about was if I have area, if I ever stop, right? If I ever stop, that's finite, isn't it? I go a little further, that's finite. But if I go forever, is it possible to still be finite? That's kind of like, I don't know. This should help you, I guess, convince you that it might be possible that that area is finite. It might be. If I draw a function that looks like this, let's say I draw a constant function, goes forever, and then I ask you to find the area under that. Is that going to be finite or infinite? Infinite, right? That's like a rectangle that goes forever, and it's just, that would be an infinite area. But this, we don't know. It depends on the function. It depends on if it's going towards the x-axis and how fast it's going towards the x-axis. So there's a lot of things we don't know. All right? So this, this thing here, the notes here, this idea of an infinite interval, we have to figure out a way of doing a problem like this. So before I give you the notation, what we're going to do is this. Draw a picture for you. Sorry, I have to go here. So what about this? What do you think about that? Think about a container again. And don't even care if it's 1 cup or 2 cups, whatever it is. I start pouring stuff in. I pour in half a cup, 1/3, 1/4, 1/5. I do that forever. Does it overfill? These are getting smaller, right? So is it the same thing that happened last time? Does it asymptotically approach something? No, this is actually infinite. This overfills the cup. Why? It's how fast these are getting small. So in chapter 8, we have to study what it is that makes things get small enough, like what is the thing that controls whether or not this thing blows up to infinity or actually converges to a number. Chapter 8, stay tuned. For now, we want to do this. Our goal here is to take some function f, try and find this area. So the way we're going to write this is we're going to go integral a to infinity of f of x dx. So that's the notation change, right? Notice that the right endpoint, this goes forever this way. All right, so since I want to go forever and see what the area is, I'm going to go from A, which is my starting point here, A, and I want to stop never, okay? I want to go forever. Right, but how do we do that? Infinity is not a number, right? Infinity is an idea. So what we do is this. We change this integral, leave a space in the front. I change this integral to go from A to t. So that would be finite, right? If t is a number, that's a finite answer. We definitely have some finite number, yes? But I want to see what happens when t gets bigger and bigger and bigger, right? So I'm going to take the limit of this, and I'm going to let t go to infinity. That is the definition of an improper integral of type 1 when your interval is from a to infinity. So when we have from a to infinity, and we want to do this improper integral of type 1, infinite interval, we do this integral, which turns into this limit that we have to evaluate. Now remember from Cal 1, limits, sometimes they don't exist, right? Sometimes they don't exist. If this limit turns out to not exist, then we're going to have to say something. We're going to have a term for it. If the limit does exist, then we're going to have another term for it. Let's just get to it though. All right, let's do an example. Well, yeah, okay. Yeah, no, let me give you let me give it to you now. So if this limit exists, we say the integral converges to whatever the limit is, okay, to that number. So if you take this limit and you actually get a number, right, a numerical answer, then we're going to say that this integral converges to that.